Thanks, Simon. Before I begin, I just wanted to make an announcement because I'm not sure it's been done yet. There's going to be an informal meeting at 7 here with some wine and cheese to talk about Sean's account of the early universe in the low entropy state. I think that Khalil wanted people to sign up at the registration desk if you're going to be there, so he knows how much wine and cheese to get. Okay, that's at 7 this evening. Okay, so I'm going to give a somewhat more philosophical talk than some of the previous talks. First, I remind you this discussed remark of Feynman's, which I mostly agree with. I don't think philosophy is going to help figure out what dark matter is or what dark energy is or anything like that. But I do think there are some questions that come up in physics that philosophy does have at least opinions about, and that I'm going to talk about one of them. And seeing Hawking the other night reminded me that of his remark, and I'm going to talk a little bit about this, basically this question, and some philosophical views about it. So if you think about the distinction between physics and philosophy, when you're asked, at least when I was asked this by a journalist here, I was thinking about how to distinguish physics and philosophy, and here's a way to make that distinction. Physics is in the business of figuring out what the laws are and what the probabilities are. And it's amazing that so much can be done without having answers to these philosophical questions. What are laws and what are probabilities? But in fact, physics proceeds without answering those questions. And this is why philosophers are paid so much. They get the very difficult question. Okay, so it's important to distinguish those metaphysical questions from epistemological questions. Sometimes they can get run together, but George Ellis reminded us to keep our metaphysics and epistemology separate, and that's very good advice. So if you ask the question, how do we know what the laws are? Well, that's answered in terms of scientific methodology, which physicists, learn at their supervisor's knees, I guess. The question of how we know what laws are, that's more difficult. And to give a good answer to that, I mean, philosophers have ways of arguing and presenting pictures and counterexamples to proposals and so on. But I'm not sure, I don't have a comprehensive, anything like a quick answer to what the methodology of philosophy should be, and that'll come up a bit in this discussion. Okay, so one thing that you might start with is think about the origin of our concept of scientific law. It's an interesting thing that historians of science, as far as I know, haven't really investigated to the extent that it could be the history of the concept of a scientific law. There's no book-length treatment of this that I know of. But it's a more or less dominant view is something like this from what I can gather. It's that the concept of law was introduced into early European science in the 16th, 17th, 18th centuries by sort of a combination of ideas from theology and from geometry. So the idea is that on the one hand, laws comprise a system that describe the motions of material bodies, something on the line of Euclid's axioms and description of geometry, and also that laws are principles that God employs to govern the motions of material bodies. And at least in some of writers at the time, Newton in particular is very vivid, it's just because the laws are imposed by God that they have the ability to explain the motions of material bodies. But of course, as physics developed, the role of God as governing the universe through laws was sort of dropped out, although the metaphor of governance remains, and you hear now everybody, physicists or even physics textbooks, talking about laws governing motions. So here's a famous remark by Laplace indicating that he thought the notion of God dropped out. Okay, so if we think about laws now, how they're thought of, and when philosophers think about laws, one thing that's useful to do is to think about what kinds of features lawful equations. Laws are represented by equations. What kinds of features lawful equations have? And while there's a little bit of philosophical jargon, in that jargon that philosophers have gotten to use, most of this is pretty self-explanatory. So I'm not saying that everyone who's thought about this agrees with all of it. They don't. But the general view is that lawful equations have to be true. It's generally thought that they're contingent, so they might not have been true. That they fit into a system of laws, so they're part of some systematic theory. That they have certain other features. They're relatively simple and natural, whatever that might amount to, that they exhibit symmetries, involve conservation principles, and so on. So there are some signs of lawfulness. That they're enormously informative, and particularly informative in a certain way by specifying how the state of a system evolves to the future or the past, or specifying the probabilities of the evolution of state. Laws also determine a distinction between initial conditions and laws, or involve in the distinction between initial conditions and laws that determines the notion of physical possibility. And most importantly for this discussion I'm going to have is that they ground explanations, and clear to explanations they support counterfactual statements, like if the system had started out in this counterfactual state, it would have evolved in such and such a way. And they ground causal relations, so there's some close connection between causation and lawfulness. And one thing that philosophers are very interested in often is the relationship between the kinds of reasoning we use, from evidence to hypothesis, and it seems that laws may do play an important role there. Okay, so here's what the central metaphysical question about laws are. It's really what I think the way Hawking put the question is, what in reality, in what exists, makes an equation a lawful equation in addition to its being true? That is, what enables a law to explain, reliably predict, support counterfactuals, ground causation, and so on. And I'm going to talk about two views about that, two answers to that question that you can find in the current philosophy of science, or the metaphysics of science literature. One view I want to call the governing view, and it's the view that laws of physics are metaphysically fundamental elements of reality, and that produce and govern and thereby explain the evolutions of physical systems. The other view I'll call the summarizing view, and a particular version of it I'll talk about, called the BSA account, that means best system account. And that's that laws of physics are certain theorems of a scientifically best systematic summary of the physical facts, the motions of particles, fields, and so on throughout all of space and time. So the governing view has been held by a number of people. So Tim has really the nicest and the most, I think, clearly developed account of a governing view. And it's that laws are really part of reality. They're sui generis elements of ontology, in some sense of ontology, if you have a very broad sense of it. In some way, they're things. They exist contingently, and they govern the evolution of the state of the universe, or the state of a system. And that the explanatory power of laws derives from their governing the evolution of the system state. So obviously there's a similarity between this and this governing aspect of the early conception of laws. We'll come to that in a little bit. What about probability? Well, laws and probability go together with each other, and in fact, objective probabilities seem always connected to laws. They come in with the laws. And how to think about probability is an important, interesting question, also a philosophical question, one that scientific practitioners of the sciences don't really need an answer to. They know how to use the notion of probability, but we might want to know what exactly are probabilities. And one view about this that goes together with a governing view is the so-called propensity view. It's usually associated with Popper, but other people have developed it in better ways than Popper. and these are the probabilities that occur in indeterministic laws. And the idea is that just as a deterministic law governs the evolution of state, a probabilistic law in some way, I don't know what to say, it guides the evolution of state or nudges the evolution of state, just not in a deterministic way, but by a degree. There's a propensity or a degree of propensity for a state to evolve from one situation to another. An interesting thing that about the governing view is that if you really take seriously the idea that the laws take the state and evolve it to another state, it looks like you're taking seriously at a very fundamental metaphysical level the idea that time has an intrinsic direction in it. And this is something that Maudlin holds. It sometimes has a more flamboyant metaphysical characterization. So George Ellis was talking about an evolving block or growing block conception of time, which fits in well with this conception of laws, because you can think of the laws taking the state or what's been settled already and producing the next state, which isn't real until the laws have operated. So you can think of time as being associated with this growing block of reality. Okay, so if you look at the way laws are talked about in physics, I've done this a bit at this conference actually, is to ask physicists, what they think laws are, and you get different kinds of answers. But if you just look at the practice of physics, it seems to fit in with a governing view pretty well, in the sense that if you're thinking about how to employ laws or the lawful equations that express laws, the typical employment is to set initial conditions, use the laws, and then use the laws to evolve the initial conditions, as though the laws were governing the evolution of state. And physicists often have or it can easily be brought to have the opinion that different sets of laws could lead to evolutions for certain states, which lead to systems going through exactly the same sequence of states, even though the laws were different. And if you have this view, then you think of the laws as something over and above the states, the sequence of states. And so laws seem to be some part of the ontology then. And some cosmologists have an even, a more, I want to put a notion of law like this to even more use. So Krauss and Vilenkin, I was reminded when Jim Holt mentioned them the other night, who want to explain why space-time and its physical contexts exist in terms of laws existing in some sense outside of, or I don't know, prior, if that's a word you could use here, are also seem to be appealing to something like this governing view. Okay, so I don't like the governing view very much. It's not because I don't like theology, but that doesn't appeal to me. But I do think that the governing view has as an aspect of it, or it's the intuitions that lead to us to think of laws in those terms, ultimately have a kind of theological, at least background to them. But here's what I think of as the real philosophical problem, is that once the governor, God, who in the early conception of laws was thought of really as something like a physicist, because he liked to have laws that are simple and natural and exhibit symmetries and so on. Once that's taken out from the concept of law, the question becomes, really vivid. What exactly is this governing notion? Governing without a governor is puzzling, and of course it was puzzling even with a governor, at least to most people. And it's even more puzzling for probabilistic laws. How exactly do the laws guide the evolution of state? Also, the intrinsic direction of time that seems to be required by the governing view, I think is a vivid metaphysical idea, and there are arguments, I think good arguments in some respects, to want to take it seriously. But in fact, I think it leads to more trouble than it's worth. And the main problem I think of is that it's hard to see how it should be connected with entropic accounts of temporal asymmetries of the sort that were talked about earlier this morning. I'll come back to this point later on. Okay, so there's an alternative account of laws, and a completely different account of what breathes fire into the laws. On the governing account, what breathes fire into the laws, well, in its theological version, it's God who breathes fire into the laws. That's not something I think that Hawking would be happy with. On the non-theological version, it's just taken as primitive or basic, that laws are entities that have this fire in them. On this Humean alternative I'm going to tell you about, which is a summarizing or descriptive account of laws, insofar as you want to continue this metaphor of breathing fire into the laws, it's something like, the answer would be, well, it's the world, the facts of the world, and physicists, or physics, or the community of physics. So the idea is that the physicists themselves are the fire breathers. Yeah. So here's what the Humean alternative is. It takes as the basis that the universe consists of something like a space-time, or something which plays a role of an arena. Maybe it's something more primitive than space-time, but some sort of arena which has a certain kind of structure, so we can talk about a distribution of entities of certain kinds, particles or fields or strings or whatever, throughout the space-time. And just to give a name for it, I'll call it the Humean mosaic. This is a term that the philosopher David Lewis, who proposed a view that like this, used. And the idea is that laws now are just certain descriptions or certain regularities of the Humean mosaic. The job now is to say which ones are those, which regularities are those. So Lewis's version, which he also attributes versions like this to John Stuart Mill and to Frank Ramsey, he called the best system account or best system analysis. And here's his idea. He says, imagine now that you had big books that listed the uncountably infinitely many propositions that describe the history of the universe, or the contents of the universe, the field values of the various points in this space-time structure and so on. And think of this big book, and then try to axiomatize it. Think about axiomatizing it. Try to find a systematization of it. Of course, it might not have any kind of good systematization from our point of view, but maybe it does. So think about these systems. Maybe some systems are pretty good. Maybe some are good because they're very informative, or they exhibit the kinds of symmetries that physicists has come to like. Some are good because they're simple. They can be expressed in terms of Lagrangians or whatever. And so think of all of different systems and imagine them competing against each other. And one, or maybe more than one, we could think of as best systematizations. They're the ones that best balance the virtues that the community of physicists look for in a final theory, a good systematization of the world. Now, I'm not saying that anybody literally does this. Of course, nobody does this, or that we know or anybody knows what this systematization is. It's kind of an ideal, a regulative ideal. So the best system is an ideal that physics aims for. But it may be that even if there is a best system, it'll never be known, either because of failure of imagination of the physics community to think up the best system, or because there are only access to whether or not a system is true or not. Truth is a requirement on best system, is via experiment and observation, and it may be that there's a great deal of underdetermination, so different candidate best systems are observably equivalent, but one of them is right and the other's wrong. Well, we may never be in a position to know that, which one is right. So I think that physics operates under an assumption that there is something like a very good best systematization. And so far that assumption seems to have been vindicated, fairly spectacularly if you look at it in an optimistic way from Newton through the development of relativity and the development of quantum mechanics and quantum field theory. Although right now some people think of physics as going through a bit of a crisis about whether or not there will be a very good systematization of particle physics. But there's no explanation within physics about why there is a best system of our world. That's just not something that physics can do. Physicists can propose candidates for best systems or partial, what will fit into a best system, partial accounts. But there's not going to be an explanation within physics of why the world has a best system. I don't think there's going to be an explanation of that from anything. I think it's something that just brings us out of the arena of explanation. Although, some people think that there are theological explanations of this, but I don't see that they're really get us anywhere or satisfying. And there certainly aren't going to be philosophical explanations. So there's no guarantee from philosophy that the universe has a best system. Rather, this is, I think, a guiding assumption of the practice of physics. Okay, so one of the things that I think is very attractive about this view is what it has to say about probability. I know from early on as an undergraduate, I was very puzzled about how to think about probability. And there's an account of probability that fits right in with this best system account. I'm just going to sketch it for you so you get an idea. But it's not unfamiliar. Sometimes even probability is introduced with words like this. But think of probabilities as not items in the world, in the ontology exactly. Rather, probability notion is introduced into physics, as it was introduced in physics, especially in the 19th century, as a device for producing a better summary of the facts about the universe. Better in this way, that by adding a probability function to your description of the universe, one can have fairly simple laws that are highly informative in the way probabilistic claims are informative. So just think about this in the very simple way of, in which you have a great deal of information, let's say about the outcomes of coin flips or something like that. It's extremely random looking. If we were to be very informative about those outcomes, it would be very complicated. If we were to be very simple, we wouldn't be very informative. But if you say, well, look, this has a certain probabilistic structure of a Bernoulli process, then you might be able to be both very informative and simple together. Good. Okay, so I like this account very much. For one, as will come up in a little while, in I think an important way in its consequences for cosmology, is that this view about probability allows for a probability distribution over initial conditions, because it might be that by introducing a probability distribution over initial conditions, one can increase the informativeness of a system by adding not very much complexity. And I think this is a way of understanding, let's say, the probabilities in statistical mechanics, as I'll talk about a little bit more in a while. And let's say in those versions of quantum mechanics that have deterministic dynamical laws like Bohmian mechanics. So it's a question of, often it's said that the probabilities in Bohmian mechanics are ignorance probabilities. Well, all probabilities are in some sense ignorance probabilities because they don't give all the information, they give some, and we use probabilities in a way to determine what we should believe, or our degrees of belief. So in that sense, they represent ignorance or knowledge, however you want to look about it, degree of belief. So all probabilities are like that. And within Bohmian mechanics, there are actual facts that are the actual trajectories of particles in a system, which are not being represented by the probability distribution. The probability distribution is a distribution over possible configurations. But they give information about it. Good. This account of probability provides a reductive, not an eliminativist, but really an reductive account of physical probabilities. These are objective physical probabilities. In some sense, it's similar to frequency accounts, but in some sense different also. Frequency accounts require a type of event that's repeated over and over and over again. This account can apply to specific events. And frequency accounts, always have to have probabilities turning out to be rational numbers. There's nothing about this account which requires that. So on this account, this best system account of probabilities are objective but contingent and a posteriori. And that's in contrast to some other ideas that I sometimes appeal to in talking about probabilities that appear within deterministic theories, like in deterministic statistical mechanics and Bohmian mechanics, where people sometimes appeal to a principle of indifference. So I think that's not a good idea, and it can get you into trouble, as I think David Wallace pointed out at the end of his talk. And most interestingly is this. So here's the kind of question that a philosopher would love and probably a physicist would hate. We all think probabilities should guide our degrees of belief. So a philosopher would ask, why is that? What is it about probabilities, objective physical probabilities, such that we should have our degrees of belief match those probabilities? So that's a principle that we probably at least have formulated in a more precise way, a principle that we all go along with. But what is it about physical probabilities that make that principle a good principle to go along with? Why should our beliefs match them? Well, I probably won't go into this very much, but I'll just say that in fact I think this account lends itself to a nice story about why it is that physicists, once they make the commitment that the universe has a best system, why that they are also going to be committed to matching their degrees of belief to the objective probabilities given by what they think is the best system, or some averaging over what the candidates for being the best system. Okay, so I think this conception of probability has some consequences for cosmology and quantum mechanics. So it applies pretty naturally to Bohmian mechanics, as I mentioned before, and to the GRW account. In the GRW account, there are dynamic probabilities, but the idea there is if the facts of the world fit in with a wave function evolving in accordance with the GRW account, so that the best system of the world includes that dynamical law, then that dynamical law is the law on this account because it's the best summary, and it's the best summary which employs indeterministic, probabilistic laws. So it gives a good account of probabilities, dynamic probabilities like that, or initial condition probabilities like in Bohmian mechanics. It doesn't easily apply to the Everett account, though, which is one of the reasons that I'm skeptical of the Everett account. It's just because there are no well-defined frequencies in the Everett account, whereas this best system account really does depend on there being well-defined frequencies. Everything happens in the Everett account. Now, I'm not saying that there isn't some other story that might be told within an Everett account, and of course, David and Simon and Sean here now have endeavored to give that sort of account. But anyway, I'm just pointing out that it doesn't really apply very well to that kind of account. And one can get worried about its application to the multiverse for somewhat similar ideas. And I do think it's come up, and it's come up here a few times, of the question of how exactly should we make sense of probabilities when there are infinitely many possible universes in which everything happens that can happen, does happen. And so these other accounts seem to require some additional principles, either principles in the metaphysics, and God knows what they might be like. In fact, let me re-say that. Only God knows what they might be like. And, or principles of rationality. And I'm skeptical, like indifference principles, I'm skeptical that those are going to be really defensible, but that's a long discussion. Okay, what about this best system account in time? So its connection to time is rather different from the governing view. So the best system account presupposes, in some sense, a four-dimensional block account of space and time, since we want to talk about the laws. And what are the laws depends on the whole distribution throughout all of space and time of the field values and particle positions and whatever it is that constitutes the universe. And so it's literally incompatible with a growing block account. Although maybe you could somehow, well, anyway, it doesn't fit very well with a growing block account. And it has no need for time to have an intrinsic direction. That might be a good thing if one's puzzled by what this intrinsic direction of time could have come to. So then it opens up the idea of trying to characterize the temporal asymmetries in a scientific way in terms of statistical mechanical laws or some other way like that. So it fits in with an entropic account of temporal asymmetries like the kind that the two Davids were talking about earlier. Okay, but it's open to a lot of philosophical objections, and some of you probably, these have occurred to you already. I mean, basically, it's very deflationary looking compared to the governing account of laws, and that might get you worried. So one worry about it is that on this view, whether an equation is a law will depend on physicists, really, on the community of physics. Of course, it depends on the world, because it depends on what the facts are, but it also depends on what's counted as simple, natural, symmetric, and so on. So I've grown to actually like this feature of the account rather than dislike it, but for some it'll make it all seem too subjective. But I think our concept of law, after all, it is a concept that developed within physics to give explanations and developed by physicists. So I think that you can at least I've come to not be worried about its subjectivity. Of course, it's not subjective in the sense that if you see a giant rock hurtling towards you thrown out of a 10th floor window, you can't just change your criteria of simplicity by yourself and keep the rock from hitting you. In fact, you can't keep it from hitting you at all. The most you could ever do is to keep it from hitting you as a matter of law, if that makes you feel any better. But you can't even do that because, the kind of story that I want to develop here is one in which its being a law depends on something like what's implicit in the practice of physics and the whole community of physics. Because this may change somewhat over time. That was a point that was brought up, I think, in Carr's talk, though he had very different metaphysical views from the kinds I'm talking about here. So the laws are objective on this account, so since they depend on the patterns actually present in nature, but they have this other relative to physics feature. But I think the main objection to this account is just this, that because on the BSA account, laws don't govern the evolution of state, they're really incapable of explaining the evolution of state. So the answer, which would take longer than I have time to develop here, but the basic idea, although I'll talk about one of the specific ways in which you make that objection in more detail in just a second, but the basic thing is that on the BSA, the explanatory power of laws and their role in supporting counterfactuals and grounding causation and so on derives from their unification, that they unify the patterns in the universe, and that this gives them. This is where the fire comes from. So, of course, to develop this idea, you need to develop particular accounts of counterfactuals and causation that fit in with this account. But I think that's possible to do, and I've worked on this, and many other people have as well. So here's a way of putting forward what I think is the real, that's bottom of the complaint from people who don't like this view. So this is a quote from Tim Maudlin's book. You have two hands, I see that, Simon. That's good, I think 10 minutes will do it. Includes discussion. In that case, I'll rush a little bit, so a little discussion. Okay, so anyway, look at Tim's complaint here is that since in some way the Humean mosaic, what I've been calling the Humean mosaic, accounts for what the laws are, the laws then can't turn around and explain anything in the Humean mosaic. But I think that this objection can be deflected in this way. Go from here. By making a distinction, which I think is important for philosophers at any rate, between metaphysical and scientific explanations. So it's right that on this account, the metaphysical explanation of why the laws are what they are has the Humean mosaic as being prior or first. But that doesn't prevent laws from being used in scientific explanations in the usual way. That you derive the evolution of state from the laws and other facts about the state. Good. Okay. Oops. So one of the payoffs for this account of laws, I think, is the way it fits in with the scientific explanation of temporal asymmetries of the kind that David and Carlo and various other people have brought up here. And that is that the second law of thermodynamics and other temporal asymmetries can ultimately be explained by a kind of package that involves a probability measure over the possible initial conditions of the micro-initial conditions of the universe, and a boundary condition specifying the entropy of the universe at the time of the Big Bang, what has come to be called the past hypothesis. And this idea can be found in numbers of people, but originally in Boltzmann and Feynman and David Albert and Sean Carroll here. David and I have come to call this the Mintaculous. Should have asked him before whether I was allowed to reveal this, but that's what it's called. But he's published it also, so I guess it can be. So you know where the term comes from, the Mintaculous? It's a very nice movie by the Coen brothers, in which one of the characters, a minor character who's sort of a nebbishy guy who spends all of his time in his pajamas working on some big project, is asked, what is he doing? And he says he's creating the Mintaculous. And he's asked him, what is the Mintaculous? And the answer is, it's the account of the probabilistic structure of the world. Well, that's what this yields. This yields the probabilistic structure of the world. So with a little bit of whatever, we adopted this name for it. This provides a general system which is fairly simple and gives is highly informative about macroscopic regularities and macroscopic laws, and particularly those of thermodynamics. And it does this without introducing a metaphysical feature of time into the story, which I think, in fact, I know George Ellis likes this kind of account a lot, and some other people do here too. But I think if they ask themselves exactly how is this arrow going to engage our brains, or how the growing block is going to engage our brains, to really give an account of the what's going on in our brains, so that when we have the appearance of the passage of time, I think they'll be stymied, actually. At least I don't know of any account like that. So, I don't think metaphysics can give explanations of that sort. Anyway, and I think also the Mintaculous account provides, as was sort of suggested, I'm not sure David Wallace would quite go along with this way of putting it, but he was making a connection between special science regularities, which tend to be temporally asymmetric and involve causation. And I think that they're grounded in the probabilities of the Mintaculous, and I think that there's hope of giving a good account of which correlations are causal correlations by starting with the correlations that the Mintaculous provides you and looking, anyway. So this is a very grandiose picture, so appropriate to bring up in a cosmology event, I guess. This is the theory of the world, the Mintaculous theory of the world. Of course, big question mark here. What exactly does count as a state, a microstate of the universe? Well, we don't really know that. What really counts as the dynamical laws? Well, this is for physics. That's why philosophers are working on the other problems. Okay, so two questions. This probably is pretty obvious now that this is what I think here and where this is going. Two questions that come up within statistical mechanics, and that is, what's the meaning of the probabilities? Well, I've already given a story about that. A dynamical account of the probabilities doesn't seem to be appropriate for statistical mechanics if we think of the underlying laws as deterministic. And the principal indifference account leads to big puzzles like Penrose's account, as David Wallace mentioned earlier today. And in any case, the principles of indifference run into all sorts of contradictions and troubles and problems. So I think this gives a much better account of what the probabilities are there. The other big question is, what's the status of the past hypothesis? So that's what we're going to talk about with Sean later this evening. Let's go back to that. So when the past hypothesis is added to the dynamical laws and the probability distribution, it increases the informativeness of this package enormously in a certain way. It allows one to make grounded inferences to what's gone on in the past, explains why there are records, explains why we can influence the future in certain ways, but not the past in certain ways. And so I think that on the best systems account, it qualifies as a law because it's part of the best systematization of our world. But if you do think that it's a law, then Penrose's complaint that it's so unlikely is sort of based on a mistake. It's based on his idea of thinking that there's some other law, God's law, in which God is randomly picking an initial condition of the universe, and it has a very low probability that he picks that one. In fact, pretty much anyone he picks, very low. Anyone he picks will have a low probability. But if it's really thought of as a law, then it doesn't have a low probability. If the probabilities that we actually use in physics, the objective probabilities, come from the best systems account, then the probability isn't low. In fact, it's 1, in just the same sense that the dynamical laws have probability 1. It has the same status as that. Now, this might not appeal to some physicists because we're not used to thinking about initial conditions as lawful, although it's been brought up as an idea a few times here. But on the best systems account of laws, well, if you find it attractive, you'll have no trouble counting a constraint on initial conditions as being lawful. Good. Okay, so my conclusion about this is that cosmology seeks an account of what the fundamental laws in the universe, and philosophy of cosmology is interested in what fundamental laws are. But I presented a couple of accounts of this. The governing account, I think, is unsatisfactory, or it needs much more discussion than I went into. But I wanted to put it in the light of the history of the concept of law, which I think makes it more plausible that you could question the concept of governing laws, particularly if one removes God from the laws. And told you a bit about the BSA account, which provides a non-governing account of the law that fits well with this Mintaculous proposal and with other theories that posit boundary conditions and initial condition probabilistic laws. Okay, thanks.
Okay, we have about 2 or 3 minutes. I'd like to stick to time. Because we do have a round table afterwards, we can come back to Barry's talk there. So just 3 minutes. I'll take 1 question, 2 questions, 3 questions. That's it. Sorry. So you first.
A very rapid comment and a short question. So the very rapid comment is wow, I'm a physicist, and I've always insisted on the utility of philosophy for physicists, and that's the kind of things I would like from philosophers to hear. I mean, that's
the kind of thing philosophers like to hear too.
Oh, well, okay. Thank you. We can go out for a drink then together.
We can stop there.
Yeah, I've always been sympathetic with a sort of Hume view of laws rather than a governing one. This makes enormously sense, everything you said to me. It just may put orders in my thinking, especially for what regards probability. 2 points which are dear to my heart. One is relational quantum mechanics. That's exactly the kind of probability that this best system account view of probability, which perhaps might work there. But the second one, that's what I want to get to, is time. You nicely pointed out that this BSA account of probability, it's compatible with sort of time reversal. But I would say, and that's what I want to test you, and that's a question, it's also compatible with a theory where there is no fundamental time. And the problem I have is that the so-called Humean mosaic that was formulated by Hume in terms of things that happen in point in space-time, and has remained so in Thiem, for instance, modeling way of thinking, or in David Lewis, for instance. I mean, David Lewis has all possible worlds, except that I am a physicist. I'm trying to work out a theory of what happens when gravity is quantized, and the possible world which I'm trying to describe is not one of Lewis' possible worlds, because it doesn't admit a description in which there is a single space-time manifold on which things happen. It's more complicated. So, So the question is that, do you think this best system account can actually remain working for a theory in which a continuous four-dimensional space-time given as a starting point for doing physics is not present?
Well, in this version of it, I mean, you're right about everything you say about Lewis and so on, but I don't think it's essential to this BSA idea that one starts out with a space-time manifold already divided into space and time. And in fact, one could even give a little bit of a glimmer about why one of the dimensions in the 4 dimensions is special, because it might be that if you formulate the laws in the way we formulate dynamical laws, we get the simplest system by taking one of these as special and having the laws, be familiar-looking dynamical laws. Whether or not you could start with something with a very different structure from space and time, sure, but I don't see any way to do this without starting with some sort of a structure which gives something like addresses to whatever the fundamental ontology is going to be.
Okay, well, let's be brief.
I'll try to be, yeah. When you say, it sounds like this BSA is sort of like a maximal compression of the data. You've got all the data in the universe and you're maximally compressing it. I mean, I guess the first question, and of course, maybe it depends on the criteria, but I would have thought that there should be some theorems that one could prove that given any data, there's, well, you have to have what computer language are you compressing it, but that there should be some compression. And then the other thing I was thought is if it's really supposed to account for all of the data, I don't see how probabilities can come in. I mean, it sounds like probabilities are coming in because you're giving up precision. You're not counting for everything, but you're getting a much shorter description by just failing to actually completely describe everything. Sure. So then it seems a little bit arbitrary can you reduce the arbitrariness in how much you're deciding to give up in as far as precision of describing versus how much you gain in the simplicity of the truncated partial description?
Well, I think the last thing you said is right on, that there's gain in simplicity at the cost of informativeness. Right. That's right. But I think the idea here is that this is something that's balanced in the tradition of physics, that physicists want to have a theory. They want to have a theory which they can test and apply to local systems and so on. So there are a bunch of criteria that actually do the work of figuring out what those criteria are. That's sort of, I might think of as anthropology of physics. I don't, or that's something philosophers of physics to do. I don't have much to do that, though I have at least one student who's here who's doing some of that now. But I don't, so it's not just compression. Compression is one thing, informativeness is one thing, but simplicity, naturalness, symmetries are other things. And buying them may lead to loss of informativeness in this ideal.
Okay, look, we're about to go to the roundtable discussion. George, I promise you a first question after those discussants have had their say. Sean, I think you also had your hand up. Right, the second question. So first and second, but of the roundtable session. So let's thank our speaker now.